Today we will be learning about circuits, magnetic field, flux, and transformers. To begin, Ohm's law states that the current I is equal to voltage over resistance. Now current is measured in amps, which is this capital A we see here, voltage in volts, capital V, and resistance in ohms, which is this little half circle. Now when we see a circuit, as you see at the bottom left of the screen, we have a circuit drawn. Here you see 2 or 4 lines. The 2 long ones denote a positive charge, the 2 short ones denote the negative charge. When current flows through a circuit, so the box that you see is a wire, when it flows through the wire, it flows from positive to negative. So in other words, the current in this exact picture is flowing this way, and it'll loop back around. The spikes that we see here are the resistors, which work to slow down the current. So current, by definition, is a bunch of tiny charged particles all moving in the same direction. Resistance, you can think of blockers that stop that or decrease the amount of resistance being put through. And voltage is supplied by the battery over here. So a great analogy is to think of a roller coaster. So when we think of a roller coaster, we have a track, and we also have a wire. So if we think of the track as the wire, next the voltage is supplied from the battery, the plus minus that we said over here. So if we think of the voltage from the battery is what pushes the current through the wire. So we are going to denote that the voltage is analogous to the cart, and that the people, each individual person, will think of as an individual tiny charged particle that the voltage the cart is carrying through the track or the wire. So we'll say current is analogous to people. And the brakes, if you've ever been on a roller coaster, you know that after a large drop down, that there's usually a brake to slow things down. We can think of those as the resistor. Now, if we have 2 people, person 1 is standing, let's say right here, person 2 over here. When this roller coaster comes down, person 1 will feel a gust of wind as the roller coaster comes down. Person 2, however, will not, because they are so far away. So in other words, you have to be within a certain vicinity or certain area close to the roller coaster to feel its wind. This is analogous to magnetic field. Okay? Magnetic field is defined as a region around a magnetic material or a moving electric charge within which the force of magnetism acts. So in other words, how close do you have to be to the roller coaster? What's the area you can be in to feel the wind from the roller coaster? How close, what's the area you can be in from the wire to feel its magnetism? So magnetic field is also interchangeable with the name B field. We will see those used interchangeably. When we denote a B field, it's measured in Teslas by a capital T. So when we see let's redraw this current or this circuit. Now let's add the B field to it, the area that you have to be around to be able to feel its effect. Now, as you can see, we've drawn that as X's, which means the B field is going into the page. If we had drawn as dots or O's, we would know that the B field is coming out of the page. Now, remember, B field's not a plane, so that's why we have to know it as going into the page or behind the page, because it's an area. An easy way to keep track of all of this, as far as the direction of the current, where the B field's going, and the overall force, is the right-hand rule. So if you look at the bottom right of the screen, we have a right hand, and you see in the picture, your fingertips should always denote the direction of the B field, your thumb the direction of the current, and your palm the direction of the force. So if we were to look at the circuit we have redrawn down here, we remember that the circuit is traveling, or the current, is traveling from positive to negative, so it's traveling this way, and the B field is into the page because it's denoted as X's. So if we were to point our fingertips at the circuit and our thumb for the left side with the battery up, because the current is traveling up on the left side, we would find our palm, the force, facing left. If we orientate our hand and follow the current, flip your hand so that your thumb is now facing to the right, because at the top of the circuit, the current is traveling right, you would find that your force is now up. Keep following and you will find force all the way around. Now you'll notice that in this uniform B field there is no net force because they all cancel out. Now, keeping in mind that the wind is analogous to, or the area to be able to be standing in to feel the wind is analogous to the magnetic field, flux is the measurement of magnetic field passing through an area. So in this little diagram on the left, it says flux is proportional to the density flow. So the measurement of flux depends on how much wind in that area. Flux varies by the boundary facing the direction of flow, and flux is proportional to the area within the boundary. So to connect this to our analogy, if we were to measure flux at the top of the roller coaster versus at the bottom of the roller coaster, we would find that flux is much higher at 2 rather than 1 because there's more wind, there's more change in the amount of wind at position 2. Now in a perfect world, if we were sitting at position 1 and say there were to be a strong gust of wind, the amount of wind just suddenly changed, the magnetic field changed. We would feel the carts may, start to move, start to roll down the hill and start to travel along its track or path in the same way that if we were to change the magnetic field for a current or for a circuit, the current would start to circulate again. This creates an induced voltage. An induced voltage is an electrical potential created by an electric field or magnetic field or current. So as the air starts to flow, it might help push the carts along that is carrying the current, right? So Faraday, a famous scientist, came up with this law. It says that the induced voltage, which is this E symbol we see here, is equal to the number of loops in your coil, we'll get to that, multiplied by the change in your magnetic flux over the change in time. Now when we describe magnetic flux, we describe it as the magnitude of your B field times the area you're measuring, because remember over here in this third slot down here, flux is proportional to the area within the boundary. So how big the area you're measuring times the cosine theta, where the angle is the angle between the B field and the plane being measured. So as you see in the diagram, the plane is slightly tilted upward, creating an angle of theta that we see here. However, if that angle were 0, we would take the cosine of 0, which is equal to 1, which will be the angle we use in most cases. Okay, so here's where that letter N that we saw comes into play. So a transformer, which on your left-hand side of your screen, you should see a picture of an actual transformer. You see these connected to poles that help circulate power through the city. So by definition, a transformer is a passive electrical device that transfers electrical energy from one electrical circuit to another or multiple circuits. Okay, so what does that mean? So the picture we see, it says a transformer is a passive electrical device. So it's transferring electrical energy from this circuit to this circuit, from your primary to your secondary. Okay? And since there's one power source, the rate that the power is supplied to both of these coils is the same. Therefore, ratios between the two coils can be set up. So the ratios here are as follows. The induced voltage of coil 1 over the induced voltage of coil 2 is proportionate to the current in coil 2 over the current in coil 1, which is also proportionate to the amount of turns in coil 1 over the amount of turns in coil 2. And since in the E that we see in this first green box is voltage, we could also say that the change in voltage is also equal to the amount of turns. When using these ratios, it's important to keep track of which value for which coil. So in other words, you see that coil 1 is at the top here, but it's at the bottom in this ratio. It's important to keep track of these ratios and know which numbers go where. So let's try to apply all of these ratios, ideas, and concepts to a problem. So the problem says that a soldering iron uses an electric current in a wire to heat a tip. The transformation with 100 turns on secondary coil provides 50 watts at an RMS voltage of 24 volts. So let's start by giving ourselves a picture. Okay, so part A asks, what is the resistance of the wire in the iron? Simple question, we can use Ohm's law. So part A, we need to rearrange the equation to solve for R. However, now we have a problem. We don't have the current I to solve for R. So if you remember earlier, we said that the power supplied to both coils is the same. And if we take into account what power actually is, it is the amount of energy transferred or converted at a time. So if we were to think of it in terms of power is equal to what's put in, the voltage, over what's lost, the resistance. And now we can solve for power. So power, we are given the voltage of 24. We plug in our values. So now we will solve for R. We get 11.52 ohms. However, we need to account for significant figures, so we will round it to 12 ohms. Now for part B, it asks us how many turns are in the primary coil. So we need to use one of our ratios. So since we are already given voltage 2, the amount of turns in N2, and we're solving for N1, we will use this second ratio in the second green box. When we multiply that out, we get the following, solving for N1. Now, you may notice we're not given V1. However, we can take into account that the primary voltage is that of a regular stock outlet voltage, which is 110 volts. So when we plug in those values, we get that 458, but taking into account significant figures, we round that to 460. So part C asks, what is the current in the primary coil? Now that we know the amount of turns, we can use a different ratio. However, we do need to solve for the current in the second coil. So using the resistance from part A that we solved for and the voltage given to us, we can use Ohm's law and solve for the current in the secondary coil. So we find that the current in the secondary coil is 2 amps. We will now plug that into our ratio and solve for the current in the primary coil. We've already plugged in our values, so we now get that the current in coil 1 is equal to 460 over 100, which is 4.6, and we will multiply that by the current of the secondary, which is 2 amps, and we find that the current in the primary coil is 9.5 or 9.6 if we round for significant figures, 9.6 amps. Okay, so we'll put our answers over here in a box just to clean things up a little bit.